Okay. So hello. So for this first one, we have this function f that goes from a, which is this. Oh, 1 second. Sorry, YouTube was playing in the background. And then b. So first, we're going to show that this function is one-to-one. Does anyone want to tell me what we need to show for this to be one-to-one? So just start with the definition of that.
Isn't it like we need to show that the domain and the codomain are like the same?
No. So to show a function is one-to-one, we want to show that for every element over here, so this is our codomain, we want to show that each element in our domain goes to exactly one element in the codomain. So what we want to show is that in this case, say we have AB. So AB is a parent A, then if f of AB equals, and also we have a, say, CD in A. So if this equals CD, then AB equals CD. So basically, you're saying that for every element over here, if you have something coming to an element like this one, any arrow here is coming from exactly one element in the domain, is what you're trying to prove. So does anyone have an idea how to start this one? So we'll apply the definition to this right here. So we say 2 to the A times 3 to the B is equal to 2 to the C times 3 to the D. And then we can do some manipulations here. So we can divide both sides by 2 to the C, and we get 2 to the A minus C. And then we can divide both sides by 3 to the D. We get 3 to the B minus D. And this is equal to 2 to the 0 times 3 to the 0, also equal to 1. And so if we look here, the A minus C equals 0. And from here, we get B minus D equals 0. And these imply that A equals C and B equals D. I'm going to have to check on that. What are you doing? So this shows that for every element in the domain, there's exactly one element, or every element in the codomain, there's only one element in the domain that goes to it. Does that make sense? Questions? Yeah, so what happened? My cat is being insane. Really big, loud noise, maybe something broken, I don't know. So is that good? Yeah.
In the lecture video they did a problem similar, and they said something about the 2 and 3 are primes.
Yeah. Okay. Yeah. That 2 and 3 being prime are important. So we know that since 2 is prime, it can only divide 2 over here. It can't divide 3, right? Because 2 only divides 2, right? As a prime number. It doesn't divide any other primes. Good question. Anything else? Okay, so what we want to show for this one is that it's onto. And does anyone want to remind me of the definition of onto? So graphically, what we want is something like this. Yes. Well, kind of, sort of. So Lance says each element in the codomain is also in the domain. That's not quite right. What we actually want is that every element in the codomain, yeah, has an element mapped to it. So there's a element in A that gets mapped to every element in B. So when we write that formally, we say for all B in B, there exists I'll just do A comma C in A, such that F of A comma C equals B. Okay, and I'll give you maybe a minute or two to work on this on your own before finishing. You'll want to use this fact right here that 144 is can be written as 2 to the 4th times 3 squared. Okay, does someone have an idea how to go at this? Okay, so for every B, we can write it as, right, so we know that these are the elements of B divide 144, which means that it has to be part of the prime factorization. It has to divide the prime factorization. So we can write every element as B as 2 to the X and 3 to the Y, right? And since 144 is 2 to the 4th, so we have 2 to the 4th times 3 squared. The powers of 2 that can divide this are 2 to the X, where X is in 0, 1, 2, 3, or 4, right? And the powers of 3 that can divide this are 3 to the Y, where y is an element of 0, 1, or 2. So if we look here, we can see that our domain A is a cross product of these two sets. So this means that everything from A is going to divide B, which means that, or everything mapped from A is going to divide 144. So there's everything that divides 144 has a pre-image in A. There we go. That's the correct statement. That is absurd. Does that make sense? I feel like I didn't explain this very well.
And then if I understand, there'll be like maybe a couple dots or numbers in A that don't have to lead to B, but what needs to be on to is that everything in B leads from something in A.
Yep. So, we could have any number of dots over here just as long as these go to something in B. That's all we need for onto is that everything here is covered. Good question. Any other questions?
I'm a little confused on how we use the prime factorization of 144 rule. I didn't fully
Right.
understand that.
Okay, so we know 144 equals 2 to the 4th times 3 squared, right? So if we look just at the powers of 2 right here, what can divide 144? The powers are 0, 1, 2, 3, or 4, right? And if we look at just the powers of 3 that can divide 144, we get 0, 1, or 2. And so this says that, okay, so everything in B can be written as a number that divides this by uniqueness of prime factorization, right? So as long as x is less than or equal to 4 and y is less than or equal to 2, then it will divide this, right? So this is the element of B. So every element of B, looks like 2 to the x times 3 to the y. And we showed that that we can every element of A has a way to get there. Does that make sense?
Yeah. Is that how you're going to leave the answer though? Is this like your final work? Is this work?
I would have written it more Englishy on homework. So, okay. We know that, so we know that B is equal to 2 to the x times 2 to the y, right? For every B and B. And we know from prime factorization that x, so from prime factorization, x, yeah, 3 to the y, sorry. So x is in 0, 1, 2, 3, or 4. And y is in 0, 1, or 2. So these are both by prime factorization. And since both of these sets right here are equal up here, so 0 A equals 0, 1, 2, 3, 4, product with 0, 1, 2, then we can find something in A that maps to B. So then there exists C and A, such that FAC equals B. Does that make sense?
Yeah, that makes sense. Thank you.
Yep. Thanks. Okay, so so this one asks, using parts A and B, what can we conclude about the cardinalities of A and B? So what does onto tell us? So if we remember our picture, the codomain, so it's onto, the codomain can be smaller, right, than the domain. So this tells us that the number in B is less than or equal to the number in A. All right. And then if we look at the picture for 1-to-1, so let's say there's 5 elements in the codomain and 3 elements here. The fact that it's 1-to-1 tells us that the number in A is less than or equal to the number in B. So since we have that it's both onto and 1-to-1, we can say that the number in A equals the number in B. Right? Oh, one other thing I want to mention about the doing onto. Usually when you're doing onto, you're going to be constructing an inverse function to show that you can find an element in the domain to go to the codomain. So yeah. Any questions on this? Okay. So for this one, we have 2 relations where we have A, which is the set of English letters in the alphabet. And then we're going to decide if it's reflexive, irreflexive, transitive, or antisymmetric. So let's begin with reflexive on relation 1. So relation 1 says that for all pairs of letters in the product of the alphabet with itself, alpha immediately precedes beta in alphabetical order. So does someone want to remind me of the definition of a reflexive property? Yeah. So for every A in A, we need to show that A is an R1. So is this true? Yeah. Every element has an arrow. So does anyone want to guess whether this is true or false? Yeah, false. And it's false because, for example, the letter A does not precede itself. Okay, so for irreflexive, so this one's not quite the opposite of reflexive. So for this one, we're saying for every A in A, the pair AA is not in the relation. So does anyone want to venture if this one is true or false? Yep. This one is true because no element precedes itself. Yeah, not an element of R1. Thank you. No letter precedes itself. And then transitive. Does anyone remember what transitive means? So in what case would something not be reflexive, but also not irreflexive? Okay, yeah. So I'll just draw an example relation with the arrows. How about the last letter Z? It doesn't come before itself either. So, so if we have a relation like this, two elements, one has an arrow to itself. So let's just call this 1 and 2. And one doesn't have an arrow, then this one is not reflexive or irreflexive. Yep, correct. It's because of this for all. So that's the reason not opposites, because this needs to be, the opposite of this is there is exists. Yeah, good question. And yeah, I saw someone give the definition of transitive. So for every A, B, and C in A, if A and B are in the relation, and B and C is in the relation, then AC is in the relation. So I'll just change these to R1. So I'll give you a minute to think about that. This one's a little tricky. You want to think about this immediately precedes thing. Yeah, so I'm seeing some answers that are right. Yep. So the example from chat is that A immediately precedes B, and B immediately precedes C, but A does not immediately precede C. So this is false.
So how does that apply in this relation thing here? Because we only have alpha and beta.
Yeah, so alpha and beta are elements of the product of the alphabet with itself. So, it's the pairs like A, B, AC, so on. Is that your question?
Yeah, I think so. But then we just said that this is like, what, not transitive? But doesn't A come before C? So isn't that kind of true? Oh, wait, that was about preceding.
Yeah, it's immediately precede. So only B immediately precedes C. Yep.
Okay.
There's only so many problems I guess you can come up with. And then finally,
have a question.
Yeah.
So this is just more of a question about writing proofs, but since this is a set of English letters, is it not right to use English letters as variable names?
Yeah, so what we'd want, okay, that's a good point. So that's the reason they were using alpha. So I guess alpha, beta, gamma, alpha, gamma. Does that help?
Yes.
So alpha, beta, and gamma. Thank you.
Why does A not precede C? Because wouldn't it, if the rule is AXA, I feel like you would have a rule where A precedes C.
Yeah, so A does not immediately come before C in alphabetical order, right? Right. So we have A, B, B, C, C, D, and so on. But we don't have A, C because A doesn't immediately come before C.
And so the only reason it's not transitive is strictly because of this example where it's alphabetized. Okay, thank you.
Correct. What if we're on an exam and we don't know what the symbol for gamma is? I mean, if you use the same letters, I mean, you could just make up a symbol. You're not going to have one of these on an exam, so I'm not going to require you to do this. So yeah, but as long as you're clear what you mean, you should be fine on an exam. Yeah, I think those are the questions. And then finally, we have antisymmetric. And does anyone want to remind me of the definition of this? So we have for all alpha and beta, yeah. So if we have alpha, the pair alpha beta in R1, and alpha does not equal beta, then beta alpha is not in R1. So is this one true? I'll give you a minute. Yeah, okay. I'm seeing some people that are done, so, and the answer is true, right? Since if alpha immediately precedes beta, beta does not precede alpha. In this case, it doesn't really matter that the alpha and beta are different because the constraint that alpha and beta are different doesn't really matter because none of them are in the relation if they're the same, because there's no reflexive elements here. Any questions on this? Okay. So for this one, I'll just we'll move through this one faster. So we have R2 is the pairs alpha and beta in the product of the alphabet with itself. And here we have alpha comes before beta in alphabetical order. So is this one reflexive? Yeah, so this one is not. And so if we remember, this is for all alpha in the alphabet. Alpha is in the relation. And so A does not precede itself, or it does not come before itself. So this is not in the relation. Irreflexive, so this one was for all alpha in A. Alpha is not in R2. So yep, this one's true. And that's because no element comes before itself. Yep. And then transitive. Yep. And so this one is for all alpha, beta in AA, and beta, gamma in AA. Alpha, beta in the relation, and beta, gamma in the relation implies alpha, gamma in the relation. So what makes this different from the last one? If anyone wants to venture. Yeah, so we can show A comes before C. And in fact, A comes before X, so we have A, M, and M, X, and then we have AX in the relation. Yep. Everyone good with that? And then for anti-symmetric, we have for all, yep, for all alpha beta in AA, A product A, alpha beta in R2, and alpha does not equal beta implies beta alpha not in R2. So you can remember this one as, for every arrow between distinct elements, you don't have a backward arrow. So that's how you remember this one. And this one is true, and that's for the same reason. So, if A, comes before B, B doesn't come before A, for example. This one's kind of weird because, it's kind of hard to be formal about the order of elements in the alphabet. Okay, so any questions on this? Okay. Okay, so we have this relation where you have pairs from the integers, and they're in the relation if, so if we have x, y in integer product integer, x minus y is divisible by 3. So let's show reflexive. And I'll just write the definition and give you about a minute to solve it yourself. For all x in integer, x is in R. Yep. Okay, yeah, it looks like people are done. So we need to show this. So if we look at the definition of R, we want to show that x minus x is divisible by 3. So we're showing that x minus x equals 0, and that's equal to 3 times 0. And 0 is an integer, and that means that 3 divides x minus x. So therefore, x is in our relation, and that means that it's reflexive. So that's reflexive. I did that. So for symmetric, I'll write the do we need 0 as an element of z or of the integers? Technically, because the definition of divisible by 3 is that you can find an integer that equals x minus x. Yeah. I wouldn't take off points for that though, but I mean, that's the reason it's true. So for all x, y in the integers, if x, y is in the relation, then y, x is in the relation. I'll give you about a minute or two to solve that. Okay, looks like people are done. So does anyone want to get started? Yep. So from X, yeah, I'm seeing the right ideas in chat. So if X and Y are in the relation, so we'll go and expand that definition. So this means X and Y are in the relation. That means that 3 divides X minus Y. And if we apply the definition of divisibility by 3, we get X minus Y equals 3 times M for some M in the integers. And then if we multiply both sides by -1, we get -1 times X minus Y equals -3 times, -1 times -3 times M And then if we apply this, we get y minus x equals, I'm going to move the negative in front of the m. So 3 times negative m. And right here, I'll write negative m is an integer by closure of technically plus, or of multiplication. Yeah, multiplication. Okay, and then this right here means that 3 divides y minus x. And this is the definition of y minus x, yx being in the relation. So this means that yx is in R. And so R is symmetric. Everyone good with that? Okay. And then this last one is transitive. So for this, we're showing for all x, y, and z, not in R, in the integers. X, y is in R, and y, z is in R, implies x, z is in R. So I'll give you, I guess, 2 minutes to work on this. Yep. No idea? Okay, so we'll start by applying the definitions to our assumptions here. So x, y is in R. That means that 3 divides x minus y. And that means that x minus y equals 3m for some m in the integers. And yz being in R implies 3 divides y minus z. And that means that y minus z equals 3n for some n in the integers. Yeah, you can send, if you type in chat, just send it to everyone. If you want to read the chat, that's fine. If you don't want to see answers, don't read chat. And so Brendan suggested that we add these two together. At least I think it was Brendan. Yes. So if we add these two together, we have x minus y plus y minus z equals 3m plus 3n. And so these two cancel out right here. And so we get x minus z equals 3m plus 3n. And then we can do x minus z equals 3 times m plus n, and that's by the distributive property. And then we can say x minus z equals 3l, where L is an integer by closure of plus, and L equals m plus n. So this means that 3 divides x minus z, and that implies xz is in the relation, so R is transitive. So that's all you need to show is, get over to here and you're done. Everyone good with that? Yep, okay. I think this is the last one we're gonna do. So the partition is based on the elements that are equivalent to each other. So just to make this a little concrete, I'll say P of 0 equals the set with 0. So can someone tell me some other elements in here? P of 1 is the set with 1 in it. P of 2 is the set with 2. So remember that we're looking for elements whose numbers whose difference is divisible by 3 or has a remainder of 0 when divided by 3. I'll give you maybe a minute to think about this. Yeah, so just think about where, like, the numbers that are in the relation with 0, the numbers that are in the relation with 1, the numbers that are in the relation with 2. Yep. Okay, so if we look here, I was doing this suggestively, but like 0, 3, 6, 1 and 4 and 7, 2 and 5 and 8, so on. So P of 0 is equal to the set of x in the integers such that 3 divides x. P of 1 is equal to integers x such that 3 divides x minus 1. So this corresponds to the remainder being 1 when divided by 3. And P of 2 is equal to the integers such that 3 divides x minus 2. And this has remainder of 2. So maybe just quickly we'll check this is a partition. So we know they're not empty, right? Because this one has 0 in it, this one has 1, this one has 2. We know they don't have elements in common because the division theorem says that every remainder is unique. And the only way you can be in here, for example, P1, is if the remainder is 1. So nothing else can be in. Nothing can be shared between any of these. And the division also tells us that when you divide, every integer equals 3 times n plus r, where n is an integer and r is in 0, 1, or 2. So this is a partition of z, of the integers. Any questions on that? Okay.
Why did you do 0 through 1 and 2?
Why did I do that? Where?
Like you did P0, P1, P2.
Yeah, so these are the three sets that make up the partition. Does that make sense? This is by the equivalence relation.
Oh, okay.
Yeah. So P0 is the set of integers that are divisible by 3, right? So like 0, 3, and 6.
Mm-hmm.
All of these are related to each other under the equivalence relation. P1 is the set of integers with a remainder of 1, like 1, 4, and 7. And these are all pairs of these are in the equivalence relation, and so on.
If you were dividing by like 5, would you have more?
You would have 5.
Okay, yeah, okay, gotcha.
Yeah, and that would just be from the remainders.
Right.
Maybe that'll show up on a quiz. I don't know. It could be a hint. Although your quiz isn't for like, what, 2 or 3 weeks? So. Can you have more time for the quiz? I think the solution to that is to require less time for you to take the quiz. Yeah. I will agree that maybe the quiz was maybe a problem too long. Yeah, I'll go with that. So, I don't know, this next one, we have a best of 5 tennis match between players A and B. And we write an ordered list representation where the letters A and B indicate a set 1 by player A or B, respectively, where the first letter refers to the first set, the second letter to the second set, and so on. So, for example, if I have A, B, A, B, A, this means that A won the first set, B won the second, and so on. What do you mean lowest problem? Oh, well, I don't know if we're going to truncate quiz 3, but we'll discuss quiz 3 tomorrow. Yeah, so the first one says, how many ways are there for the match to end after 3 games? So we're looking for this list right here, right? And so if we look up here, best of 5, best of 5 means you've A or B won greater than or equal to 3 sets, right? So in order to win this, what are the options here? Does anyone have an idea? You can just yell it out.
A wins all 3 or B wins all 3?
Yep, that's a good one. So B, so there's 2 ways to do this. And then rapid fire will do this one. How many ways are there for A to win in exactly 4 ways? So in an exactly 4 games, I think this is meant to say sets, but. So in order for you to win in exactly 4 games, A had to have won in the 4th set. Otherwise, it wouldn't have been 4 sets. So we're looking here. And we know, yeah, so there's three ways. We have AAB, ABAA, and BAAA. So that's 3 choose one way. Is that the notation? We use 3 choose 1, don't we? Equals 3. And that's because if we look at the list here, we know that A1, so there's 2 A's over here, so we're just finding where this one B goes. And then does someone want to tell me why this is the same as, well, let's just fill in the blanks here. So how many ordered lists of length this taken from the set with A and B in it have exactly this many A's? Does anyone have an idea on that? So we're looking right here.
How many ordered lists of length 4 taken from A, B have exactly 3?
Yeah, that's close. Remember, we had to have A right here because of the winning in exactly 4 games. So that's why this problem is a little tricky, because this isn't part of the list we're constructing. So we have a list of length 3 right here. And it has to have 2 A's for this exactly 4 game win to occur. A good suggestion. And we're very almost out of time. In fact, we're over by 8 minutes. This one is largely the same problem. So A wins in exactly 5 games, so it looks the same, except we have 4 slots here before the final A. So we're putting like an A here and here. Yeah, so we know that A can't have won in 4 games, so there can only be 2 A's right here, because A is now winning on the 5th game. So we know there's 2 A's in this part. So yeah, 4 choose 2. So we're out of 4. How many ordered lists of length 4 taken from AB have exactly 2 A's is what we're looking for. And that's 4 choose 2. That's 6. Everyone good on that? Any other questions? Okay. That actually is the end of the slides. So, come to office hours if you have questions and whatnot. Thank you for coming.
Thank you.
Yep.